Descartes died in 1650. The war in Europe was over, Germany lay in ruins, France was triumphant. England, having executed its king, Charles I, was a republic. Over the silent battlefields settled a peace born of exhaustion. In the universities and learned societies, by contrast, the gravity wars were poised to begin. Isaac Newton was 7 years old. By the age of 11, he was ranked the second worst pupil in his class at King's School in Grantham, Lincolnshire. At some point, however, possibly in reaction to his bullying by the third worst pupil, he threw himself into his studies, which drew him to Cambridge University's Trinity College. Like Descartes, he preferred his own company, the better to work without interruption. Truth is the offspring of silence and unbroken meditation. Unlike Descartes, who died in Sweden, he never left the country of his birth. Indeed, Newton barely left the university, and he was still at Cambridge when, 25 years later, and now the Lucasian professor of mathematics, he published his greatest work, The Mathematical Principles of Natural Philosophy, usually called, after its original Latin name, the Principia. The world had seen nothing like Newton's system before. It had the scope of the most ambitious physics, such as that of Aristotle and Descartes, the mathematical exactitude of the best astronomy, such as that of Ptolemy and Kepler, yet its core could be written down in a handful of simple formulas: Newton's 3 laws of motion and his law of universal gravitation. Whereas Descartes held that all physical causation is by direct contact, Newton appealed to a force of gravity that pulls one object toward another massive object, apparently without any intervening mechanism. Many of his contemporaries saw in Newton's new force a gaping theoretical hole. How could gravitation be taken seriously unless there was a physical means, such as currents of interstellar fluid or collisions with tiny particles, to make it happen? Causal forces between planets made no sense without a tangible thing or stuff connecting them, communicating a pushing or a pulling or some other kind of visceral oomph. The notion that causation could happen otherwise, that one planet could simply act on another at a distance, as though extending a ghostly grip of arbitrarily long range, seemed preposterous. The mathematical and metaphysical prodigy G.W. Leibniz, writing around the time that Newton issued the second edition of his magnum opus in 1713, dismissed Newton's theory as barbaric physics, testimony to the sad fact that people love to be returned to darkness. In the decades after Newton, however, the idea of action at a distance, of celestial bodies influencing one another's movements across empty space with no connecting causal links, became familiar and acceptable. If anything, it was causation by collision that seemed suspicious. Why should two objects, coming into contact, refuse to interpenetrate? Some sort of repulsive force operating at a very short range must prevent them from overlapping. If so, what appear to be genuine impacts are in fact merely unconsummated flirtations with physical contact. Particles do not literally touch, but at most come extremely close before irresistible countervailing forces fling them apart. When the great German philosopher Immanuel Kant wrote about physics a century later in 1786, he claimed that it was incomprehensible that objects could act on each other except by way of brute forces, projected across space in accordance with something like Newton's law of gravity. As I have related the story so far, this sounds like yet another chapter in the chronicle of explanatory relativism, yet another example of intellectual history as a series of discontinuous jumps from one explanatory framework to another. In the 17th century, causation had to be communicated by contact. Anything else was darkness. Around 1700, according to the relativist story, Newton successfully pushed Descartes' conception of legitimate explanation aside, substituting his own, just as Descartes had earlier routed the Aristotelian approach to explanation. From then on, contact looked philosophically incoherent. Action at a distance became the only logically acceptable way to make things happen. That's how Kuhn spins the history of gravity in The Structure of Scientific Revolutions. But his relativist interpretation is wrong. Newton did not change his age's conception of explanation, but rather something deeper still. He changed its conception of empirical inquiry. To understand how, let us take a closer look at Newton's own interpretation of his method, laid out in a postscript to the Principia's second edition of 1713. There, Newton summarizes the fundamental properties of gravitational attraction, that it increases in proportion to the quantity of solid matter and decreases in proportion to distance squared, and then continues, I have not as yet been able to deduce from phenomena the reason for these properties of gravity, and I do not feign hypotheses. For whatever is not deduced from the phenomena must be called a hypothesis, and hypotheses, whether metaphysical or physical, or based on occult qualities, or mechanical, have no place in experimental philosophy. It is enough that gravity really exists and acts according to the laws that we have set forth, and is sufficient to explain all the motions of the heavenly bodies and of our sea. In this famous passage, the essential aspects of the iron rule make a decisive appearance in world history. Look at what Newton says about the mechanism for gravitation. You can see at once that he was not an ardent promoter of action at a distance. He allows the possibility that gravity is affected mechanically, by contact or collision, and also the possibility that it is affected by occult qualities, that is, by some form of non-mechanical causation, such as action at a distance, the kind of thing that philosophers such as Leibniz found to be no more intellectually respectable than witchcraft. The mechanical and occult possibilities are, in this passage, put entirely on a par. Both are mere hypotheses. We presently have no way to tell which, if either, is true. It does not matter. What does matter is that gravity is sufficient to explain, with great quantitative accuracy, the observed phenomena, the orbits of planets, the paths of comets, the cycle of tides, and the arcs of deadly projectiles. To a philosopher such as Descartes, this modest proposal would make no sense. Gravity cannot explain anything unless it passes the test for being a genuine explainer, the collision test. To put the Cartesian view another way, to explain something means grasping its cause, and to grasp its cause means to comprehend the sequence of pushes or collisions that bring it about. Without that comprehension, there is no understanding, no real explanation. Newton, by contrast, pioneers in this passage a philosophically far shallower notion of explanation, on which a phenomenon is explained simply by deriving it from the causal principles of gravitational theory, that is, from the mathematical principles laid out in the Principia. Shallow explanation does not require the explainer to grasp the implementation of the principles. More important still, it does not require the principles to pass any philosophical test or to conform to the explanatory prescriptions of a Kuhnian paradigm. Gravity might turn out to be transmitted by impact, but equally it might turn out to be authentic action at a distance. Either way, Newton maintains, we have a sufficient explanation for the purposes of empirical inquiry, or as Newton calls it, experimental philosophy. Newtonian explainers, like Popperian falsifiers, prove their worth by conforming closely not to intellectual precepts, but to observed phenomena. The shallow conception of explanation thereby frees scientific theory builders to try just about anything, however ideologically abhorrent, in their attempts to explain the phenomena. With this act of liberation, Newton escaped the endless circles of explanatory relativism and gave scientists a timeless, ahistorical criterion for explanatory power to serve as the raw material for an iron rule that dictates, in turn, a fixed criterion determining what counts as a legitimate empirical test. A scientific theory postulates some causal principles. What it explains is whatever can be logically derived from those principles. That is a standard for explanation that means the same thing in all places and all times. To appreciate fully what is objective and what is subjective in scientific practice, however, we need to distinguish more carefully than Newton did between theories and theoretical cohorts. Theories, as you now know, explain very little on their own. Very little can be derived from a theory without the assistance of auxiliary assumptions. Einstein's or Newton's theories of gravity, for example, did not on their own predict the positions of the images of stars on Eddington's photographic plates. For that, Eddington needed to add information about the positions of the telescopes, the times that the photographs were taken, the positions of the stars themselves, the assumption that the telescopes were functioning correctly, and certain theoretical posits about light. When surrounded by statements of background conditions and other hypotheses such as these, a theory forms a theoretical cohort and generates specific predictions and explanations. The iron rule's Newtonian criterion for shallow explanatory power applies to cohorts rather than to bare, unaccompanied theories. It provides an objective and ideology-free test for whether a cohort explains a phenomenon. Can the phenomenon be derived from the cohort's causal facts and principles? Aristotle's centralizing urge, Descartes' democratic jostling, Newton's matter calling to matter across empty space, each qualifies as a causal principle that might make sense of gravitation, and each is warmly welcomed into science. All the iron rule asks is that such principles and their cohorts entail what is actually seen to occur and nothing that is seen not to occur. The modern scientific standard for explanation is as empirically demanding as it is philosophically lax. Is the ineffable Aristotelian psuche scientifically admissible as an explanatory construct? Provided that it can be supplied with auxiliary assumptions to form a cohort that has definite observable consequences, yes. Even if psuche is in some sense unintelligible to the 21st century mind, from the iron rule's point of view, it is a potential scientific explainer all the same, just as long as its causal implications are, in a suitable theoretical context, explicit and sufficiently detailed. Though permissive, the iron rule's conception of explanation is nevertheless not a matter of anything goes. The Atlantean view of explanatory power does not qualify. Rhymes won't get you scientific glory. Your theory has to tell a causal story. By the time Newton died in 1727, it was already clear that he was, even among the great luminaries of the era, something special. At his funeral, the pallbearers were dukes, earls, and the Lord Chancellor of England. The young French Enlightenment thinker Voltaire, who was present, reported that he was buried like a king. Tributes to his brilliance lit up the 18th century with verbal fireworks. The Scottish philosopher David Hume described him as the greatest and rarest genius that ever wrote for the ornament and instruction of the species. Voltaire held him to be the greatest genius that ever existed. The Marquis de l'Hôpital, a French mathematician, supposedly went further still. Newton was a celestial intelligence entirely disengaged from matter. Such intimations of near divinity had begun with a poem that Edmund Halley wrote for the first edition of the Principia, ending with the line, "No closer to the gods can any mortal rise." The English artist George Bickham put the words into pictorial form in a 1732 engraving, showing Newton as the sun surrounded by angels, muses, and putti. Around the same time, the Venetian painter Giovanni Battista Pittoni conceived his Homage to Newton, in which an angel and the goddess of wisdom Minerva lead a procession of muses to Newton's shrine. A Rococo confection featuring a colossal urn containing Newton's ashes and a reconstruction and commemoration of the optical experiment in which he used a prism to split light into its component colours. Figure 6.4. What mattered above all for the spread of the iron rule's shallow conception of explanation, however, was not its advocate, Newton's position as foremost among scientists, not even his metaphorical ascent into heaven, but, as the historian of science Mordecai Feingold puts it, his metamorphosis into science personified. As a consequence, Feingold continues, Newtonian science became the model to emulate, the manifestation of superior knowledge that summoned all other learning to reorient itself along similar lines. To be scientific simply was to be Newtonian. So the investigation of nature changed forever. No longer were deep philosophical insights of the sort that founded Descartes' system considered to be the keys to the kingdom of knowledge. Put foundational matters aside, Newton's example seemed to urge, and devote your days instead to the construction of causal principles that, in their forecasts, follow precisely the contours of the observable world. The thinkers around and after Newton got the message, one by one. 3 centuries later, the iron rule's shallow conception of explanation continues to push science forward. There is perhaps no better illustration of its curious effectuality than the story of how the rule confronted the most perplexing scientific theory in history, quantum mechanics, and swallowed it whole. We come to life suspended in fluid. We are then born into a world of solid things. These 2 ways that a substance can be, solid and fluid, have directed the scientific imagination from the earliest days. When Thales, around 580 BCE, hypothesized that the world was made of water, he opted for fundamental fluidity, as did his pupil Anaximander, who suggested air, which is also a kind of flowing stuff. The ancient Greek atomists, by contrast, thought that solidity lay at the bottom of it all, that every kind of matter, even water and air, is made of tiny, rigid, indivisible particles. The two views can be combined as in the four-element theory of Empedocles, the Sicilian. Everything, he said, was composed of some mix of air, fire, earth, and water. Descartes, much later, found a different way of mixing solid and fluid. Matter is rigid by its very nature, but comes in many sizes, the larger chunks making up solid matter like the planets, while at the other end of the scale, particles that can be infinitesimally tiny constitute a kind of dust that, like a fluid, flows into every available nook and crevice. In the 19th century, more exotic forms of fluid and solid behavior were called upon to do explanatory service. As dramatized in my tale of Montague and Capulet, heat began the century as a fluid but ended it as the motion of solids, the disordered vibration of countless tiny particles. The same intellectual current revealed that gases, the most rarefied of tangible fluids, were themselves composed of microscopic solid particles traveling at high speed. Light, by contrast, was, by 1900, thought to be a wave traveling through a fluid more subtle and ineffable than any gas, the electromagnetic ether. Inspired by this idea, a small but influential group of scientists proposed to analyze all solid matter as ethereal. In the words of the German physicist Gustav Mir, writing in 1911, elementary material particles are simply singular places in the ether at which lines of electric stress of the ether converge. Briefly, they are knots of the electric field in the ether. After 2,500 years, it might have seemed that physics was sailing back to Miletus, where the ancient Greek philosopher Thales first made the bold surmise that all was liquid and liquidity was all. The ship never arrived. By the 1930s, the great conceptual and metaphysical cornerstone that was the solid-fluid duality had been obliterated. Matter, now conceived as a mix of particles, such as electrons and protons, was still in the picture, but thanks to quantum mechanics, it no longer behaved at all like the ordinary physical stuff of everyday experience, fluid or solid. It spent its days rather in a mysterious mode of being called superposition. Superposition was nigh unintelligible. It didn't matter, not to working scientists. What they cared about was shallow explanation, and quantum mechanics succeeded in that endeavor like nothing that had come before. The case of quantum mechanics, then, is the perfect exemplification of the supremacy in modern science of Newton's precept that, for the purposes of experimental philosophy, derivation of the observable is the only kind of explanation that counts. The first hints of superposition came in the initial decade of the 20th century in a series of theories designed to make sense of puzzling phenomena involving radiation and light. Perhaps the most iconic of these was Albert Einstein's explanation of the photoelectric effect, in which light striking certain substances causes the emission of electrons. Light, Einstein posited, which usually behaves like a wave, in this case behaves like a stream of particles, photons. Descartes had argued that light is made of particles. 19th century scientists had shown that it must be a wave. Now it turned out that it was not one or the other, but somehow both at once. When the first full versions of quantum mechanics were formulated in the 1920s, it became clear that it was not only light that lived a double life. Streams of electrons, universally assumed to be ordinary particles, were quite capable of behaving like waves. In fact, all matter appeared to be some sort of wave-particle chimera, as though ancient mythology had all along been truer to the hidden structure of the universe than ancient physics, as though the centaur, half horse and half man, or the sphinx, half woman and half lion, were better models of reality than Aristotelian substance or the atom. It was a philosophical emergency. The nature of reality was at stake. What was quantum physics trying to tell us about the world? The question was intensely discussed in letters and in lab corridors, most of all those of Niels Bohr's Institute for Theoretical Physics in Copenhagen. Bohr was an enthusiast for quantum mechanics, which he had helped to pioneer. Einstein was a skeptic in spite of his own early contributions. The two scientists famously debated the adequacy of the theory at the Fifth Solvay Conference on Physics and Chemistry in Brussels in 1927, and then again at the Sixth in 1930. The physicist Paul Ehrenfest gave a sense of the spectacle. Bohr, from out of philosophical smoke clouds, constantly searching for the tools to crush one example after the other, Einstein like a jack-in-the-box, jumping out fresh every morning. Oh, that was priceless. Einstein had earlier written to another founder of quantum theory, Max Born. Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. 90 years later, physicists still have no alternative. It is beginning to look like quantum mechanics is indeed the real thing. The debates about its meaning continue. Yet the science rolls imperturbably on, as quantum theory has been extended since 1930 to apply to electromagnetic force, the interior of the atomic nucleus, and, though an undertaking still in its infancy, gravitation itself. That is a remarkable scientific achievement. It is also a remarkable social achievement. In the world of ancient Greece or the pre-Newtonian 17th century, competing philosophies meant competing sciences. But quantum mechanics did not split into philosophical schools. Rather, even as Bohr, Einstein, and many other key figures at the Solvay Conference in 1927 philosophized furiously, the theory remained a unified set of ideas that developed rapidly, disseminated very quickly, and met almost no resistance. The new textbooks written to explain quantum mechanics to students barely mention the disputes at all. The interpretation of quantum mechanics was, in short, considered to be so much philosophical superstructure perched on top of but hardly integral to the science below. The same is true today, yet it is not as if the strangeness of the theory is invisible to scientists. Murray Gell-Mann, the discoverer of quarks, called quantum mechanics a mysterious, confusing discipline. According to Roger Penrose, one of the late 20th century's foremost mathematical physicists, quantum mechanics makes absolutely no sense. I think I can safely say that nobody understands quantum mechanics, remarked Richard Feynman. How can a theory be widely regarded both as incomprehensible and also as the best explanation we have of the physical world we live in? The answer lies in the shallow conception of causal explanation, in which it is derivation rather than comprehension that is paramount. To inspect that answer more closely, let me take you wading in the shallows of quantum explanation. Though entirely non-technical, the overview that follows will take a bit, but I promise you that it's worth your time. What we'll see is a contrast between the obscure nature of superposition and its clear consequences. The natural philosophers, such as Aristotle and Descartes, cared about the consequences of their theories, causal principles, of course, but they also cared a great deal about their nature, about what the principles were saying about the metaphysical foundation of the world's causal structure. Modern science, by contrast, is oblivious to the principle's nature. Let it be as opaque as action at a distance was to Newton's adversary Leibniz, as Aristotle's psyche is to us. It is immaterial. All that concerns the iron rule is what kinds of things the causal principles are capable of bringing about. I will show you how quantum theory derives accurate predictions from a notion, superposition, that is quite beyond our human understanding. Matter, says quantum mechanics, occupies the state called superposition when it is not being observed. An electron in superposition occupies no particular point in space. It is typically, rather, in a kind of mix of being in many places at once. The mix is not perfectly balanced. Some places are far more heavily represented than others, so a particular electron's superposition might be almost all made up from positions near a certain atomic nucleus and just a little bit from positions elsewhere. That is the closest that quantum mechanics comes to saying that the electron is orbiting the nucleus. As to the nature of this mix, it is a mystery. We give it a name: superposition. But we can't give it a philosophical explanation. What we can do is to represent any superposition with a mathematical formula called a wave function. An electron's wave function represents its physical state with the same exactitude that, in Newton's physics, its state would be represented by numbers specifying its precise position and velocity. You may have heard of quantum mechanics' uncertainty principle, but forget about uncertainty here. The wave function is a complete description that captures every matter of fact about an electron's physical state without remainder. So far, we have a mathematical representation of the state of any particular piece of matter, but we haven't said how that state changes in time. This is the job of Schrödinger's equation, which is the quantum equivalent of Newton's famous second law of motion, F equals ma, in that it spells out how forces of any sort, gravitational, electrical, and so on, will affect a quantum particle. According to Schrödinger's equation, the wave function will behave in what physicists immediately recognize as a wave-like way. That is why, according to quantum mechanics, even particles such as electrons conduct themselves as though they are waves. In the early days of quantum mechanics, Erwin Schrödinger, the Austrian physicist who formulated the equation in 1926, and Louis de Broglie, a French physicist, both eventual Nobel Prize winners, wondered whether the waves described by quantum mechanics might be literal waves traveling through a sea of quantum ether that pervades our universe. They attempted to understand quantum mechanics then using the old model of the fluid. This turned out to be impossible for a startling reason. It is often necessary to assign a wave function not to a single particle, like an electron, but to a whole system of particles. Such a wave function is defined in a space that has 3 dimensions for every particle in the system. For a 2-particle system, then, it has 6 dimensions. For a 10-particle system, 30 dimensions. Were the wave to be a real entity made of vibrations in the ether, it would therefore have to be flowing around a space of 6 or 30 or even more dimensions. But our universe, rather stingily, supplies only 3 dimensions for things to happen in. In quantum mechanics, as Schrödinger and de Broglie soon realized, the notion of substance as fluid fails completely. There is a further component to quantum mechanics. It is called Born's rule, and it says what happens when a particle's position or other state is measured. Suppose that an electron is in a superposition, a mix of being everywhere and nowhere. You use the appropriate instruments to take a look at it. What do you see? Eerily, you see it occupying a definite position. Born's rule says that the position is a matter of chance. The probability that a particle appears in a certain place is proportional to the degree to which that place is represented in the mix. It is as though the superposition is an extremely complex cocktail, a combination of various amounts of infinitely many ingredients, each representing the electrons being in a particular place. Taste the cocktail, and instead of an infinitely complex flavor, you will, according to Born's rule, taste only a single ingredient. The chance of tasting that ingredient is proportional to the amount of the ingredient contained in the mixture that makes up the superposition. If an electron state is mostly a blend of positions near a certain atomic nucleus, for example, then when you observe it, it will most likely pop up near the nucleus. One more thing. An observed particle's apparently definite position is not merely a fleeting glimpse of something more complex. Once you see the particle in a certain position, it goes on to act as though it really is in that position until something happens to change its state. In mixological terms, once you have sampled your cocktail, every subsequent sip will taste the same as though the entire cocktail has transformed into a simple solution of this single ingredient. It is this strange disposition for matter, when observed, to snap into a determinate place that accounts for its particle-like behavior. To sum up, quantum mechanical matter, the matter from which we're all made, spends almost all its time in a superposition. As long as it's not observed, the superposition, and so the matter, behaves like an old-fashioned wave, an exemplar of liquidity, albeit in indefinitely many dimensions. If it is observed, the matter jumps randomly out of its superposition and into a definite position like an old-fashioned particle, the epitome of solidity. Nobody can explain what kind of substance this quantum mechanical matter is, such that it behaves in so uncanny a way. It seems that it can be neither solid nor fluid, yet these exhaust the possibilities that our human minds can grasp. Quantum mechanics does not, then, provide the kind of deep understanding of the way the world works that was sought by philosophers from Aristotle to Descartes. What it does supply is a precise mathematical apparatus for deriving effects from their causes. Take the initial state of a physical system, represented by a wave function, apply Schrödinger's equation and, if appropriate, Born's rule, and the theory tells you how the system will behave, with, if Born's rule is invoked, a probabilistic twist. In this way, quantum theory explains why electrons sometimes behave as waves, why photons, the stuff of light, sometimes behave as particles, and why atoms have the structure that they do and interact in the way they do. Thus, quantum mechanics may not offer deep understanding, but it can still account for observable phenomena by way of shallow causal explanation, the kind of explanation, favoured by Newton, that the iron rule cares about and uses to supervise modern science's procedural consensus. The theory was accepted so readily in the 1920s and 1930s because, for all the philosophical arguments surrounding its interpretation, it provided a clear and well-defined system for providing shallow explanations that had no serious rivals. Had Newton rather than Bohr debated Einstein at the Solvay conferences, he would perhaps have proclaimed, "I have not as yet been able to deduce from phenomena the nature of quantum superposition, and I do not feign hypotheses. It is enough that superposition really exists and acts according to the laws that we have set forth, and is sufficient to explain all the motions of the microscopic bodies of which matter is made." Ehrenfest would have enjoyed that. Explanatory standards change with the prevailing philosophical outlook of the age. This thesis of explanatory relativism is inherent in Kuhn's vision of scientific inquiry as a parade of paradigms, each with a different way of making sense of the world. The thesis holds a grain of temporary truth. For millennia, explanatory standards did change. As the metaphysical wheel turned, so the explanatory cogs turned with it, from Aristotelian teleology to Cartesian collision. Late in the 17th century, the philosophically unified machinery of inquiry in which the wheels and cogs rotate as one was spiked, Newton was the saboteur, and thus he was the chief architect of modern science's first great innovation. Rather than deep philosophical understanding, Newton pursued shallow explanatory power, that is, the ability to derive correct descriptions of phenomena from a theory's causal principles, regardless of their ultimate nature and indeed regardless of their very intelligibility. In so doing, he was able to build a gravitational theory of immense capability, setting an example that his successors were eager to follow. Predictive power thereby came to override metaphysical insight, or as the historian of science John Heilbronn, writing of the study of electricity after Newton, put it, "When confronted with a choice between a qualitative model, deemed intelligible, and an exact description lacking clear physical foundations, the leading physicists of the Enlightenment preferred exactness." So it continued to be, as the development and acceptance of quantum mechanics, as unerring as it is incomprehensible, goes to show. The criterion for explanatory success inherent in Newton's practice became fixed for all time, founding the procedural consensus that lies at the heart of modern science. From the raw material of shallow explanation, the iron rule was forged.